Good morning, everybody. Somebody already noticed an issue with the lecture notes. I'll fix that. Yeah, happy Friday the 13th. Okay, I'm back. Can everyone see my screen? The Zoom crashed for some reason. Okay. All right, welcome back to System Software. We're quickly approaching the end of the semester, and in fact, today is the last lecture on the compiler project. We're going to talk about control flow, how if statements and while loops are implemented. And today also marks the start of Project 4, the last part of the project. So someone says in the chat, "I'm scarred." So I don't know if you think if you mean you're scared or you're scarred by this course. Perhaps both. So remember that Project 3 extended the deadline a bit on Project 3, so due next week. Test cases. I'll ask the TAs when the Project 3 test cases are going to be released. Somebody's asking about Simple C's .s and Simple C file. So I think there was an issue with that before. Somebody mentioned this, and I had to update it on the website. So let me see if this matches the one on the website. I'll check right now. Somebody says the S output seems to have the function f take 2 arguments instead of 1. Let me check the version on the website. But none in simpleC.c. So I'm not seeing a difference now. I'd have to check in more detail to actually look inside the codes, but I'm not seeing a difference between what so somebody last checked a few days ago. Yeah, double check, and if not, let me know in office hours, and I'll fix it. I'll fix it during office hours. Oh, there's two. So somebody asked that there's two moves. That's because one is for the parameter and one is for the y local variable. So there's two local variables to this function. So it has two entries in the stack frame. One is, I think. Okay, so it is up to date. And somebody's asking about push bx, rbx. This is because of the Intel ABI, where the callee has to save rbx. Okay, so hopefully everything, yeah, so sorry for the mistake on that last week, but hopefully everything is resolved with the test, the few test cases that you have so far for project 3. And I'll ask the TAs about project 3 and well now 4 test cases. And hopefully they'll get those up soon. Let's see the current state of the grading repository. Yeah, okay, so there's no more test case yet. So yeah, so for now you can just use the couple of test cases I've given you, and of course generate your own test cases. I mean, you should be doing this anyway, but we'll give the grading script test cases as soon as we can. I'll check with the TAs on when that's happening. All right, last week we went over how pointers work in C-like languages. So does anyone have any questions about last week, about using pointers and what the corresponding assembly code looks like? If you remember, it all came down to this memory indirect addressing, where instead of moving values to and from a memory location, we moved it, or to a register, we moved it to a memory location that was stored in a register. So yeah, any issues with the simple.s, please let me know in office hours. So somebody's mentioning an issue with simple.c or simple.s right now. It's updated? Okay, great. All right, so other issues on project, or what you need for project 3, the pointers, or I'm sorry, what you need for the pointer, dealing with pointers and compiling simple.c that uses pointers, assignment, and dereference. Any questions from last time about this? Okay, I guess everybody gets pointers. That's good. That's amazing. It's one of the trickier parts of C, and then compiling it makes it even trickier. Okay, so somebody says they'll have more questions when test cases start failing, but keep in mind that yeah. So sorry for the delay on getting the grading script out for project 3, but you should be 100% writing your own test cases as you code. So don't let that hold you back on working on the project. All right, so today we're going to be going over how control flow statements are implemented. And that's the last piece that you need in order to finish project 4. So project 4, also starting today, you'll be implementing both pointer support for pointers and control flow constructs in your simple C compiler. So you can take a look at the project 4 description here. There's already several test cases for both pointers and control flow, and some of the rules for how to compile these constructs. Okay, so let's take a look at the slides for today. Okay, let's start with if statements, something that I think every programmer knows about. But let's take a look at an example that is probably overly simple, and I think everyone should know how if statements work in C. But let's take a look at this example. So the question is, what is the value of X at the end of this code snippet? So take a second to read the code and let me know what you think the value of X is at the end of this. So someone says it depends. Depends on the condition. So it depends on, yeah, exactly. So it depends on whether this con variable evaluates to true or evaluates to false. In C, can anyone tell me how Boolean variables work in C? 0 or non-zero, 0 or 1, 0 or non-zero, good. So C doesn't actually have a Boolean type like, well, it doesn't have a Boolean type like most languages does. Yeah, instead there's a header file called standard bool. And so the way the C standard defines bools, which I can't remember if it's part of the C standard or not, is to use a type def, use a special type def that really is just an int behind the scenes. Okay, good. So everyone knows how if statements works. Let's look at the kind of informal description of the behavior of this. And so somebody's mentioning that the Gerber talks about 1 is not actually true. It's really non-zero. That's true. And you'll actually see, once we see how conditionals are implemented, you'll see why that's actually the case. And it's actually what's true about a lot in the C language is that it's kind of a consequence of how assembly language works. In some sense, C is almost like a high-level assembly language, a low-level programming language, but a lot of its behavior is really just a consequence of a fairly straightforward translation into assembly code, or at least an attempt to be very close to the way the machine works. Okay, so pretty simple semantics informally to if statements. You first evaluate the condition, and then you only evaluate and run the statements in the body if that condition is true or non-zero. Pretty straightforward, right? Okay, so in assembly, the way we implement a conditional statement is with the compare and jump idiom in assembly. So the jump operators will change the program counter or change the instruction pointer. So that if you're currently on this opcode in your assembly file, then depending on some machine state, you'll either jump to a new program counter at a different memory address, or you'll just move past the jump statement and go to the next program counter. So does everyone remember jumps or branches from CDA? I'm assuming you learned this, right? In computer architecture. All right, great. So the way these conditional statements and any control flow statements are implemented typically is basically using a jump statement, conditional jump statement. So just like functions, the machine doesn't support these kinds of nested if statements. Instead, you just have to jump past any blocks of code that you'd like to execute. And we can look at this later, but if you take a look at a bunch of nested if statements that have these nicely wrapped blocks of code, that's all just going to be one flat list of assembly code, effectively kind of like spaghetti code, just using jumps to jump around to different parts of the assembly program. Okay, and the way we determine whether the way we set the machine state to allow this jump statement to test that condition is with the compare instruction, which I'm assuming if you learned about jump, I'm assuming you also learned about compare, or whatever its equivalent was in MIPS. So the way this sequence of assembly works is you call compare, and in the Intel architecture, this sets a flag in a special register that you don't have to directly look at yourself. Instead, the jump instruction, which takes no other operands except for the memory address of the place you'd like to jump to, this jump instruction looks at the flag register behind the scenes, depending on whatever your last instruction did, and the machine uses that to decide whether it actually does the branch or does the jump. So we can actually look at the reference for these instructions, and there's a link to this in the project, to this page. Where are the? Oh yeah, jump if condition is met. So there's a whole, in Intel at least, there's a bunch of variations of this opcode, depending on what condition you want to test. And so there's this special register called eFlags that for every instruction that has some effect on the eFlags register, the architecture behind the scenes will set one of these flags. So if you run the compare instruction, the result of compare is not going to be to any particular register that you choose. Instead, it's going to set a flag in this eFlags register. And then when you go to use one of these jump instructions, it'll only jump depending on what the current state of the machine is. So the basic idiom in an Intel assembly is to run this compare instruction, and then immediately after it, use some jump instruction to implement our condition. So notice in this case, we're comparing to 0. So let's take a look at what our if statement template looks like when we're programming in C. So it's basically the same thing. We compare to 0, which, if you recall, 0 is false in our language and false in C. So the first thing we need to do is we need to take whatever that condition expression was and evaluate it. And that's basically the same thing that we saw a couple of weeks ago when we were looking at how expressions, the assembly code for expressions are how those are generated. So when it comes to an if statement, we don't actually care how that's done, as long as when we compile the if statement, as long as we know that there's some register or some location that we can get the result of that expression from. So no matter what the expression does, we just call out to the function to generate that code. And then in this case, we make sure that the result is in some register. I just picked an arbitrary register, RAX here. And then we compare it to 0. We compare this to false. So if I jump if I jump when these two values are 0, am I jumping to the if branch, or am I jumping to the not if branch or the else branch? So I compare to 0, and then I jump only if they're equal. Where am I jumping to in my code? To the not if part. So in the case of a single if branch with no else, that's jumping to the next instruction after the if statement. It's jumping out of the if statement. So what this template says is, if my code is 0, then jump past all of these other contents to the end of the if statement. Conversely, if this comparison is not 0, then this jump instruction will not jump because conditions don't hold. And so if it's not 0, i.e. if it's true, then the contents of the if branch will get executed. So for anyone who is wondering why it's 0 and non-zero versus 0 or 1, this is at least in part the reason for this. So somebody's saying AMD comparison can handle conditions like Boolean and Boolean or. So this is actually a good question. I'm going to show you later today one way to implement Boolean operations. So Boolean operations are actually distinct from bitwise operators. So if you've ever wondered why, say, logical and is different from, or how, why C has a bitwise and with a single ampersand versus a Boolean and with a double ampersand, we'll see today why that's actually the case. And it turns out that these Boolean ands and ors and nots, or at least Boolean and or, are actually done, technically, they're basically control flow statements rather than single machine operations like a bitwise and. So we'll see why that is in a bit, but let's take a look at the other control flow statements first, because once we understand those, it'll be easier to understand how these Boolean operations can be implemented. And this, of course, depends on the definition of the language and how you want to do it. I'm sure you could certainly define your Boolean operations to be logical operations under the hood, but there's a specific meaning of specific behavior in C, short circuiting, which happens because these operators are control flow operators. So has anyone encountered short circuiting in C, or did you guys learn about this? Short circuiting of Boolean and or operations. Okay, so hopefully this is clicking a little bit, but I'll get to this a bit when I talk about Boolean operators. But yeah, if you've ever wondered why short circuiting is the way it is, it's because Boolean operations are basically control flow statements. Okay, but let's get back to our if statement here. So we don't have to. So when we're generating an if statement, we don't have to worry at all about how this expression is evaluated at this point. We don't care how it's evaluated. A couple of weeks ago, we already looked at the code for generating expressions, and we can just compartmentalize that code generation inside a call to code gen expression. And just like any other, like an assignment or any other statement that uses an expression, at least for the simple C implementation I'm suggesting to you, we just put that result onto the stack and then pop it off into a register. Okay, questions so far about what an if statement, what one way an if statement can look like in assembly code? Any questions about the assembly operators or anything else? Okay, so it sounds like it's making sense so far. So one little caveat I want you to keep in mind for this and the rest of the lecture is that if you look at the C language and its behavior, and you look at assembly code, there's in many cases there's lots and lots of ways to implement the same C code as assembly. So all of the kind of templates I'm giving you today are like the first are like one simple way that will work on all of the input programs. But an industrial strength compiler will do do as much as it can to avoid branching, to use faster assembly than this kind of naive implementation. So if you compile some C program to assembly, you'll notice that some if conditions will never even branch, or some expressions will have fewer operations than the number of operations in your C code. And that's because there are all sorts of tricks in special cases where specific C programs can be compiled to faster assembly code. But there's always a kind of general way to do this. There's always a general way that'll work on all input programs. And that's what I'm going to be showing you for simple C. So that process of finding faster assembly code for particular input programs is optimization, and optimizing compiler will do this. But we're not going to talk in much detail about this in this class. But if you're interested, let me know and I can point you to locations to find more about compiler optimization. So our goal is to take the input program and not to run it, but to generate assembly code that behaves the same way, that has the same behavior at runtime for any input program. So for if statements, this is the template that'll work for any if statement we have in simple C, or really C for that matter. Okay, so let's take a look at an example of, here. So this is basically the same example that I showed you before, except I've got condition being set to some constant. Now, normally this condition would be probably read from input or something, because modern compilers can actually remove if statements that only take one branch all the time. So if they can prove that this if statement is actually not needed, you don't actually need to test it to know that the branch is always taken, then it'll optimize that away. But for our sort of simple implementation without optimization, let's just assume that we change this condition by hand, or it's an input value. Okay, so there's our input program. And assembly code, as usual, is just a wall of text. So the assembly code I've given you so far, I've generated these comments to help you walk through it. But let's dig into this, do a little reverse engineering, and just pull out the parts that make up that if statement template. So I've written a comment here for when the if statement code is being generated. And nested inside here is the code generation for the expression. So let's just ignore that for a second. We just know that we can just discharge the responsibility for generating that code to our expression code generator, which we've already implemented. And then the first thing we do is we put the result of the expression into the RAX register. So that's this second task here, store the result in RAX. And then here is our compare and our jump if equal. And then the stuff inside, we don't actually care what it is. All we do is we just recursively call code generation for a statement. And whatever that outputs, that's what it outputs. We don't actually care what it outputs. We just know that as long as we set up our template around that code correctly, then we'll have the right behavior for our C conditional. And then finally, so JE is jump if equal. That's in contrast to just jump, which is an unconditional branch in assembly. So yeah, JE is jump if equal. And it's jump if equal to this L0 label, which we put after all of the contents of the if branch. So recall, we're comparing to 0 here. We're testing whether it's false, and we're only jumping if the condition is false in this case. So we're assuming that so when the expression is true, which is non-zero, then we won't do the jump and we'll hit all of the code inside of the branch. Otherwise, we'll jump past the contents of the if branch to our L0 label. And then the first thing that gets executed after that jump is the first instruction outside of the if statement. So in our example here, this label 0 corresponds to this return expression, this return instruction. So somebody's asking, if you have two if statements, there'll be two labels. Yeah, exactly right. So our compiler is going to have to be able to generate an arbitrary number of labels on demand. And so the simple way to do it is just keep a counter and just increment that counter every time we want a fresh label. Okay, so that's the assembly code. That's the template in action. And if you ever look at compiled code, you may be able to start seeing some of these, some of code that you can tell is probably from some sort of if statement or some sort of control flow statement, because it has this hallmark of a compare and jump in it. Okay, let's take a look at this example from the abstract syntax tree perspective. We've got our if statement, and if you take a look at the data structure for if statement, you'll see that it has two child nodes, a cond, which is an expression, and a body, which itself is a statement. So we've got this statement nested inside of another statement. So it's this recursive relationship between statements that we saw in the grammar for simple C. You notice that a statement can consist of an if expression, a while expression, etc. And those expressions, if you look at their definitions themselves, can contain a statement. That's how we can get this nested structured behavior of language. Okay, so when we have an if statement, whoops, let me get my notes on this real quick. Okay, if we've got an if statement, then the first thing that we need to do is we need to call codegen expression to generate code for this conditional expression. And so we don't really care what the expression is inside. We don't really care what it is. In this case, it happens to be a variable access, so it's going to be some ident expression that has what did I use? The cond variable. Sorry, I'm just getting up my code here so I can see what the actual output code looks like. So for our if statement here, we just call out to the code generator for the expression. And this is going to give us our load from memory. Base pointer. So we saw this previously when we looked at how identifier expressions work. So for our compiler, and this is certainly not the only way to do it, but it's a simple way to do it, is we just load that value from memory and push it onto the stack. So if you don't remember how expressions work, take a look at that lecture, take a look at the project for that. But the invariant for our code generation for expressions is that when the very last thing that any expression, the assembly code for any expression does is to push its value onto the stack, so that we know any construct that uses an expression. For code generation, we know that all we have to do to get that value is to emit a pop from the stack. This is definitely not the only way to do it. It's not how modern compilers will do it because it's much slower, but it's much simpler to reason about generating code if we do it this way. Okay, so we've dispatched the job of generating code for the so for expressions, whenever you want to use whenever you're finished generating code for an expression, the very last thing that should be done is to push whatever register holds the value, generate a push of that register. And then whenever you generate code that uses an expression, the first thing you do is you generate a pop to get that value off the stack. Take a look at the lecture on that. I think it was like last time or two weeks ago. It's not, this is not a rule made in stone. It just makes it easier. Yeah, exactly. You push when you're done, pop when you need it. But remember, we're generating code that does this. We're not actually doing a push or a pop. We're generating code that does it. And to make it easier to reason about the equivalent assembly code that we're generating, so that we don't have to think about the entire expression, we can just think about each expression one at a time. A little kind of trick to do that is to generate code for pushing and popping to be able to kind of effectively pass those intermediate values to the parent and children expressions. So somebody asked if you're consistent about this, you can use other registers than RAX. Absolutely. So one of the benefits of this way of implementing expressions is that there's no each expression can use whatever registers at once, besides the base pointer and the stack pointer. Yeah, so I just use RAX just kind of by default. And if you're clever about code generation, you can actually avoid storing these values in memory and instead keep them in registers. You can be very clever about how you allocate registers to these intermediate values and to these variables. So if you have fewer intermediate values and fewer variables than you have registers, everything can stay in a register. Okay, so the first thing our if statement does is it generates the code for the expression. And it doesn't do that itself. So when we're implementing the if statement, we shouldn't have to reason at all about how the code for an expression is generated. We just pass it off to our expression generator. And so even if you haven't finished writing all of the expression generators, as long as, just pick one that is implemented. So in this case, I picked the identifier expression. As long as that's implemented, we'll be able to test and make sure that we get code generation for an if statement correct without worrying about how code generation for an expression is done. So this is yet another example of this, breaking your specification into components, working on them individually so you don't have to think about debugging or issues or how other parts of your software is implemented. Okay, so we generate code for our conditional expression, and then the next thing we do is we want to emit a pop to get this value so that the assembly code will get that value from the expression. So remember, this is our convention to make our compiler writing easier. So the next thing that this if statement does is it generates a pop instruction. Let me write that here. Okay, so there's the first part of our template. Let me show you the template just to refresh your memory. So we are here inside of our template. So the next thing we need to do is generate our compare and jump instructions. And this is just part of the template. We, at least for this compiler, we always just compare to 0. So we're always checking to see if it's false. And jumping if equal, that is jumping if the result of that expression is false. So at this point, even though we haven't generated the label yet, our compiler, we need to get that label. We need to make a new label before we do the jump. So we can't wait to make this label once we need to generate the actual label itself. We're going to have to generate the label the very first time that label is used. So in here, what's not really obvious from looking at the generated code is that here we've generated a new label. So let me actually write this in an assembly comment. So we actually need to generate a new label at this point before we have the jump. We need to generate that label and hold on to it because we're going to need to emit the name of that label for the location that we jump to. Okay, so there's our compare and our branch, and I realize that my J's and my semicolons look identical, which is my terrible handwriting. All right, so does anybody remember what the next part of this template is? We've generated code to evaluate the expression. We've done our compare and jump. So what's the next piece of this template that we need to emit? Recalling that this jump only happens if the expression that we evaluated turns out to be false. So somebody's saying push what? Oh, fill in the body statement. Yeah, fill in the body of the if statement. So we've generated the code to evaluate the expression. We've taken that value and compared it and emitted a jump that only happens if the condition was false. So at this point, this is the code for the body. Okay, so how do we generate the code for the body of the if statement? So somebody says it needs its own scope, maybe. So remember, the syntax says that the body can be any kind of statement. It doesn't necessarily have to be a compound statement, which is why in C you don't have to put curly braces, but it does have to be just a single statement. So a compound statement is a single statement. So that that's a good question. It needs its own scope. We got to walk through the compound statement. So okay, so if you remember, most of the other statements at this point, if you're following along in the project, are written already. So just like the expression, we don't have to care about how the specifics of generating a compound statement. Instead, we can discharge this responsibility off to another component of our compiler, the part that generates code for statements. So just like with expression, we can break this code generation problem down into these pieces. We have one piece that says, here's how you generate statements. And we give it a function, and as long as we call that function and it's written correctly, we don't actually care about the details of that. We don't care what it does if it's a compound statement. We don't care that compound statements need scope at this point. All we care about is that there is a function called generate code for a statement, and we can just discharge that responsibility onto that function. So this, I really want to drive this notion of components down and what functions really do for you. They allow you to break the problem down into separate components, and then as long as you get the interfaces between these components right, as long as you're very clear and specific about those interfaces, then when you're coding one component, that eases the burden of coding the entire project. You don't have to think about how that code runs. Yeah, so it's interesting that most people's first instinct was to think about what are the specifics of compiling a compound statement. But one main takeaway that I want you to get from this course is, if you use functions carefully, if you use them, well, maybe not carefully, if you use them with a little bit of forethought and conscientiousness, you can actually make the job of programming large stuff easier. And so if you see, someone has written a 10,000 line program, one of the tricks that makes that possible is breaking the problem down into its components and defining functions for those components. So a function is not just, well, let me put a name on a piece of code. I mean, literally, that's what it does. But I want to really get you to think about, at least seeing in this project, how we can break a problem down with well-defined interfaces for these functions. Yeah, and somebody also pointed out something that I've tried to get you to think about as well, and what Nicholas Wirth talked about in stepwise refinement, programming through stepwise refinement, is that even if you haven't completed project 3 and you haven't actually written all of CodeGen statement yet, if you kind of believe that your interfaces are the real interfaces, you just pretend that is completely written, and you don't have to care about whether that code is completely written or not. You just have to care about the interface, what the interface meaning of that code is. So if we know, or if we even pretend that function is written, that function is done, then we can write this if statement without even completing the code for generating code for all statements. And this is not only how we can break a piece of software down into components and write each individual piece as if it's almost as if each individual piece is its own program. So in the same way that when we write a C program, we don't think about how the operating system kernel works. We may not even know or care about how printf works. We just call it. We know it has a certain behavior. We can read the manual about what its inputs are and what its outputs are. Yeah, so somebody mentioned functional decomposition. I mean, this is a polysyllabic way to say break the problem down, and use functions to define the interfaces to those components of your software. And for compilers, getting compilers right, this is really, really important for getting compilers right. And it turns out that when we define the language with syntax, that gives us a natural set of components that we can implement individually. Now for this compiler, of course, I've designed it so that we can think about each individual component fairly distinctly. But of course, modern compilers will do all sorts of operations that look over the entire tree to do optimizations. Somebody brought up a really good point here, which I also wanted to mention. So this is true for everything in industry, because you may be on a team of programmers, and you don't want to have one team waiting for the other team to finish what they're doing in order to write their code. So if you can come to an agreement between multiple teams about what this interface is going to be, then they can actually both start writing code before either is finished. That you can parallelize this code effort. So this is really crucial in software engineering, and and particularly for, I really want to get this across on a really hard project like a compiler, because I think for many people who are motivated programmers, you can hack together a big program pretty effectively without actually thinking about its interfaces or components between parts of the software. But for a compiler, that's really, really hard to do. I think very few people can write a large compiler for a language without breaking it down into components, because it's such a confusing problem and the algorithms are much trickier. You have this recursive behavior. It's very hard to reason about code generation for any possible program. So this class, if any, is going to just force you to think in this components way. Yeah, so somebody said, write your entire compiler in main. And even for the toy compiler, I didn't write this. You could certainly write this in main and just use a bunch of loops, and you could do it in a very clever way. But I wanted to show you, also to show, the basics of compilers, but show you this sort of, you can break this down into, 3 functions, one for each code construct, and show how they kind of fit together cleverly in order to generate the code. And if you can get this notion done in a compiler, then you'll have no problem doing it on most programming problems, because compilers are a particularly confusing and tricky thing to do. Yeah, so somebody says going back to the toy compiler would make a lot more sense now. Yeah, so yeah, go back to it. I mean, it's a short piece of code, and hopefully it'll click a little more. But yeah, this notion of breaking problems down into components and specifying the interfaces between those essentially ahead of time, so I mean, it can be a little, you get into this problem of premature generalization if you try to have a very detailed interface. But I mean, you can sort of look at software engineering philosophy to look at this. I mean, there are ways to mitigate this where you, instead of trying to make an interface that does everything that you think it'll need, instead work from the MVP, the minimal valuable product, or whatever it's called. Start from that and just get a simple, 2 simple components. Yeah, minimum viable product, 2 simple components done, and then refactor and extend as you go on. So instead of saying, well, I'm going to take a shortcut to the finished product, this is like the best definition of the component. Instead, take the view of, well, let me incrementally define this specification of the whole program. So just like when we talked about abstraction and breaking the problem down, a better way to get to the end result is to take a little time along the way to do refactoring and extending your interfaces. And it's annoying to do that, because if you change the interface, you're going to have to change a lot of code. But that is a much more rote and simple process than boxing yourself into the wrong interface at the beginning and then having to jump through hoops to use that interface as you go along. So this is a really tough problem in computing, both in the kind of theoretical software engineering and also in industry. What is the right interface for this code that you're writing? And these interfaces are everywhere. Just like when we write a C program, you just write it in main and you don't think about how main is executed, because that's done through an interface to the operating system itself, to the kernel, and to all of the system software. And we just don't even think about it. And so somebody's talking about design patterns. This is a very popular thing that was popularized by this gang of four in object-oriented programming. It can be easy to abuse these, but the thing to do is to look at your problem and pick the right pattern for that problem. Instead of saying, well, patterns are great, so I like this pattern, let me use that. The real key there is to make sure you're using the right tool for the job. And you have to kind of look at the application, look at the domain, and say, well, what is it that I'm really trying to achieve here? And do I need this particular design pattern? Can I just use a function call? You don't necessarily need an object-oriented pattern for this. So I think, this is part of the reason why I think object orientation gets a lot of heat for some reason, or at least on, keyboard warriors on Stack Overflow, we'll give a lot of heat to object orientation. But it's really just a tool, and it's about fitting the problem to the tools that you have. But yeah, this is a good point. Somebody says it can be bad if you try to make every problem fit to a particular pattern. But yeah, exactly. It does help think about what different kind of designs that people have thought about before. And instead of having to reinvent the wheel, you can just say, well, oh, this is actually an adapter pattern or whatever it is. But these kind of patterns don't just happen in object orientation. A function is a kind of pattern as well, where you have the same piece of code that's being repeatedly executed, and the only difference is what its particular input parameters are. All right, so tangent on specification again. Hopefully this is this will echo in your brain when you're writing code in the future. And of course, not every program you write needs to have this kind of detailed specification component breakdown. But once if you go out into industry and once you're working on large projects, as somebody else mentioned, this is essential to do this because you're going to be coming into a bunch of software that already exists. You're going to have to work with other programmers. And it's crucial to be able to define these well-defined interfaces and stick to them. The benefit is that it takes cognitive load off of your mind when you do this. Because now, coming back to this example, when we're thinking about this if statement, there's no reason at this point to think about how the body should be implemented. We can just assume that function is written already because we've carefully designed our interfaces in this case. I mean, I've given this to you, the design, because we designed this, we have this interface already. So let's just reuse that instead of trying to think about what the body should look like. So somebody says, seems like many things in CS are philosophical. I mean, I guess technically everything is philosophical. But yeah, I mean, I think a lot of CS people have, it gets to, because it's such a new field, it gets to a lot of kind of some interesting fundamental ideas. So somebody points out something really important. This planning seems annoying because it seems like it'll take a long time, but it saves time in the long run. That is exactly right. This is like delayed gratification. Putting this upfront time and upfront actually turns out to be shorter in the long run. So not in all cases. If you're writing, a 50-line script, then of course, sitting there and trying to come up with the best interface doesn't matter. But this is really about you need the kind of experience to say, is this a large project where I need to do this? Or am I working at a job where if I take longer to do it, then I'm gonna be fired because they think I'm not productive. Of course, actually, if you take longer to do something and you get paid the same amount, then you've actually made more money. But you also risk just losing your job because somebody else will do it faster than you. Or is it a project where there's this component that I'm seeing is being used all the time, so maybe I should factor this out into a separate library call or a separate function? And then at that point, well, what is the right interface for that component based on all of my use for it? And so, this doesn't have to necessarily be done at the very beginning, but if you're going to take this approach of hacking it together and then revising as you go along, when you start noticing that there is these onerous interfaces in your code, or where there's repeated stuff or behavior that you need constantly, then go back and refactor the code. This is something that I'm kind of working on with one of my students. This applies to like writing and other aspects of work product. It's very tempting to think once I've solved this problem, then I'm done. Or once I've written some code, or once I've written some text in my paper that I'm writing, that I'm done. And the only thing that's left to do is, edit grammar or do some little tweaks. But actually that's not quite the case, or at least that's not what I can do. I can't produce this perfect product right away. So if there's any artists you like, musicians or film creators, I don't know for each case, but I'm pretty sure that they go back and they critically analyze their work and revise it over and over and over. I think for most, even for in creative work, artistic work, this is the case as well. You have kind of criticism and revision of that work, kind of self-criticism, to make a better product over time. And the same thing applies here, where we can't necessarily have the perfect generalization ahead of time, but we can iteratively get there. And by taking that kind of delayed gratification to push back the end result a little bit, it turns out that those steps into iterating to that end result will get you there faster in cases, or at least in cases where we have a large project to work on. It'll get you there faster. I don't want to say never do hacking. Hacking has its place, absolutely. There's no reason to sit down and make a component diagram for your 50-line bash script. There's no reason to do that. But once we get into large work products and work products that we want to work properly, like work correctly, and not, if you're working on a car software, you want to make sure that you do it the right way rather than get it done quickly. And it turns out that for large projects where they're safety critical, getting to the right product, which is a product that won't crash the car, is actually faster to do it in this careful, meticulous way than it is to hack it together and try to go back and fix things. So for any of you who have really struggled with debugging the compiler, and you've noticed that there are bugs in multiple locations, this will help you. So that doesn't mean you're bad at programming, or you're not smart enough to debug. That just means you're not lazy enough to code so that you only encounter bugs one at a time as you're coding. So that's really about this laziness as a virtue. When we looked at the 3 virtues of a good programmer, what you've actually done is you've given yourself a harder problem than you have to do. And so it's not about, oh my God, am I smart enough to debug this complicated program? It's really about, was I kind of lazy enough at the beginning to make sure that as I'm coding, there's very little chance that I'll have multiple bugs at the same time. So I know it's very hard to break yourself out of this mindset of let me code everything and then let me test everything. It's very hard to break out of it. But it's once you do that, you'll realize that coding is way, way easier. But it does take a little bit of kind of diligence and meticulousness to do that, a different kind of meticulousness to do that, and a little bit of planning ahead. But you don't have to plan ahead too much. Again, if you're spending all your time planning ahead, then you're never getting to coding. So it's this kind of balance. It's like, well, okay, I spent enough planning. I don't know any of the problems yet. Let me just code a little bit. And then once you start encountering problems, you can iterate over the planning process. All right, so lots of asides on specifications and components. Oh, okay, I'm glad you guys like this. This is really the real takeaway of this class, and that you know how programming languages work. All right, let's go back to our problem here. And before we take a break, let's finish up the code generation for an if statement. So where did we leave off? We have generated the code for our expression by dispatching it to another function that we don't care about how it's implemented right now. We just care about the interface, that it generates code, and the last thing it does is it pushes the value onto a stack. We can exploit that interface by generating a pop immediately is the first thing we do after that. And then we need to generate our compare and jump. So recall that work. In this case, the scheme that I've given you is to compare to 0. So that is check whether the expression is false, and then only jump when the expression is false, only jump if equal. So recall that in order to do the jump, we need a label. We need a label to jump to. So before we even generate this jump, we need to get a new label for this. So all we have to do is increment a counter for this. We can just have a little pattern, .l, and just always emit a number for that. All right, and so now here we're at the body of the if. So how do we, what do we do in our if statement code generator? How do we generate code for the body of the if statement? Good. We call a function we already have. I really hope somebody got that, because I just talked for like 15 minutes about components and calling out. Yeah, exactly. We just do code gen. We literally just do code gen statement. Exactly right. And so I'm not even going to bother to write out the code for this, because it's it's like in our example, it's an assignment statement. So it's whatever the code for our assignment statement is. So somebody has statement or statement list. So just take a look at the syntax tree structure. You'll see that it's a statement. And that's because a compound statement is one statement. But a compound statement may contain a statement list, but the compound statement itself is just a single statement. When we learn about programming in C, we think that an if statement actually takes many statements in a list. But in fact, it actually takes one statement. It takes one compound statement. So that's why there's these curly braces and the grammar looks the way it does, at least in C and simple C, is because a compound statement is a way to have multiple statements where a single statement is allowed. So only a single statement is allowed under an if, and a compound statement allows us to define a sequence of those statements instead. Okay, so we've got whatever. My iPad is freezing for some reason. So somebody's asking about while I refresh this screen, somebody's asking about the jump assembly command. So yeah, in Intel, you've got a whole bunch of jump commands or jump opcodes for each possible condition that you can test with the jump statement. So we'll see jump not equal as well today, but I think all we'll need is jump equal and jump not equal. Take a look at that that website in the reference manual for the reference manual for x86. So somebody's asking if compound statements have the same rules as a program. I don't actually know what that means. Can you elaborate? They have a similar syntax, but it's not the same syntax. So you can't define functions inside of compound statements, and the behavior is different because it's local local variables instead of globals. The syntax is similar though. Yeah, so as someone pointed out, take a look at ast.h, take a look at project 1 and 2 for the actual syntax. Okay, so we just call out to code gen statement, and this is going to be whatever the statement code is. We don't really care what's in there. All right, does anybody remember the very last thing we need to emit for our if statement template? This was like 30 minutes ago, so I don't necessarily expect you to remember that. Well, epilogue only deals with functions. So let me just show the template. So recall our template is to, a label after the body. So our template is to emit the code for the expression, emit the compare and jump, emit the contents of the if branch, and then emit, the very last thing we do is we emit the label after the body. And somebody mentions that allows us to jump to it if the if evaluation leads to skipping the body. Exactly right. That's the very last thing we do. And what's kind of interesting about this is we're actually emitting a label without any instruction, which is actually not valid assembly code. So the very, by only emitting a label at the end, if we were to try to take this code by itself and assemble it, we would lead to an assembly error because it says, hey, you're labeling a statement that doesn't exist. Because under the hood, this label is the address of a piece of code, and if there's no code here, no opcode, then there's nothing to jump to. So that seems like a little bit of a problem. But if we take a look at our code example here, this is what this whole section here is what gets emitted by calling CodeGen if statement. And even though the very last thing is just a label without an instruction, notice that it just fits together, like a puzzle piece to whatever code is being generated after that if statement. And even if in C, you have an if statement with nothing after it, when you look at the assembly code equivalent of that, there's always some instruction at the end of a function. There's always the epilogue at the end of a function. So maybe that's why somebody was asking about epilogue. So there's always some assembly code at the end of a function. So it's safe to do this. It's safe to, in our code generation function, to just emit the label because we know, as basically an implicit contract between the code generation functions, we know that whatever called the code generation for an if statement will always generate some instructions after it. So anyway, I think you'll sort of encounter that as you're programming this and be able to wrap your head about that in a bit once you look into this in a little more detail. All right, that's if statements. How the kind of template for what an if statement can look like if you generate assembly for it, and how we use these separate software components to ease the burden of generating code for an if statement. We don't have to think about how expressions and body statements are generated. We just have to think about what the template for if statements is and make sure that we're satisfying the interfaces to calling out to statement generators and expression generators. Questions on this? Questions on if statement code generation? It looks okay. It looks complicated. Well, it's complicated in its behavior, but this template is really pretty simple. And if you discharge the responsibility of generating the expression and generating the body off to other code generation functions and literally just ignore them, just don't think about it. Think about just the interface to it. Then, this is a function that has, the code generation function for if statements is, maybe five lines of code or something. It's a very short code. So again, this is this notion I want to get across to you that even if you've got a code program that's short, look at your algorithms class. Some of those algorithms, especially in pseudocode, might be like 5 lines long. It's the reasoning behind them that makes them powerful and makes them tricky to think about. It's that reasoning behind the code. And that's really the kind of gestalt of programming, I guess you could say, is it's the reasoning behind the code, not really the coding itself. That's the programming. It's reasoning about the computation that makes programming the challenge of programming and what makes, it's the real exercise in programming. Okay. Other questions on this? Great. Someone said every lecture they feel like their mind is blown. Okay, great. That's what well, I guess hopefully that's what education will do. I think that's what it's supposed to do. I hope. Okay, so let's take a break. I think we can actually take a near 15-minute break today. So let's reconvene at 11:30. I'll stick around here for any questions that people have for a little bit, and then I need to get some more water. So are there any questions on about the project? If you're having issues with the project or anything? No, I'm glad to hear it. Glad you guys, glad some of you are liking the class. Somebody's asking, ident expression doesn't check the global variables table. Yeah, so for this kind of simplified project, we won't have any global variables. It's just annoying to have to the way you access global variables is different from the way you access local variables. So it's just a little bit of a pain to you just switch between. You just have to check: is it a global? Now I access it this way. Is it not? Then I access it from the base pointer. So somebody mentions about architecture leaving making them not like lower level stuff. Yeah, so lower level stuff. Also, I'm not any expert assembly programmer, but it is helpful to understand at least some model of how the machine works when you're doing. I mean, it's important to understand compiled languages because what you're really writing is assembly at the end of the day, what you're really producing. So it's important to have some understanding of the architecture. Caching makes things faster, memory operations versus registers. It's useful to understand this stuff when you're thinking about your code. But yeah, from my point of view, the reason I find it interesting because I like this connection between the language and what it generates, not necessarily programming assembly myself, but just this kind of connection between the high-level language, which a machine doesn't actually run, and how it actually gets run on a machine through translation or interpretation. Oh, yeah, sorry about this. So I left in the instructions to do string constants. You don't need to do this for project 3. I think I updated the the code template to remove those to-dos, but let me see if I left that in the instructions. The page is updated. Okay, let me make sure. Okay, yeah. So sorry about that. Just get the latest template, or just ignore it because it's just a to-do. You can just delete the to-do. Yeah, I removed any global stuff, and I just talked about it in class how in C at least strings are stored. They're basically allocated statically in memory in that read-only data section. It's just a detail of like the kind of system-specific object files. It's kind of a very tedious detail of how that works. But as long as you understand that it's just a fixed memory location, and whenever you use that string, you just use that fixed memory location through a special, well, the way GCC does it, it uses this, I forget what it's called, but it uses an offset from the instruction pointer. There's a special memory addressing mode for doing it, but it's a very detailed, kind of finicky thing. Excuse me. Okay, I'll be back in a bit. Hello, everybody. So it's 11:30. Let's get back into it. Before the break, we looked at if statements, what their meaning is in simple C, how what their equivalent assembly code looks like. We looked at a template for generating this code, and we looked at how our code generator will actually do this code generation. Okay, so let's take a look at how we can add an else branch to this case. So what's the semantics of an if then else statement? How does this differ from just an if branch by itself? What's the key difference? There's an else. Also has an else branch. Is it possible to? So yeah, it's another place to jump. So that's a good way. That's a good way of looking at it. So we have a different place we jump to. So the important question is it possible for both of these branches, both the if branch and the else branch, is it ever possible for both of those to be executed in one run of the program? No, it can't be executed. Either one or the other. They're mutually exclusive. So when we generate code, we need to make sure that our code at runtime will only ever run one of those sections of code. The way we ensure that this happens is that in our if branch, at the end of it, we need to also make sure that we jump past the else branch. So let me show you what the template for this looks like. So it's very similar to the if branch template, except for a couple of differences. So instead of our first label going to the end of the if statement, instead, it jumps to the else branch. And this kind of makes sense because what did our compare and jump do? It jumped to L0 if the expression was false. So that's the same thing that we'd want to do in order to start executing the else branch. And just like before, we have the if branch right after that jump, so that it'll be executed if the statement was not false, if the statement was true. But then to make sure that we don't accidentally run our else branch, we need to jump past that else branch. So assembly language doesn't give us a way to have these nice blocks of code with curly braces and separate it out like we have in our nested structure of our language. So we simulate that behavior with a line of code that uses jumps to get around those blocks of code. So so we look at this another way. So we've got our two branches here in the same order that they appear in our input program. So here are the two branches. And we kind of cleverly set up all the labels and jumping around those two branches to make sure that only one of those branches is executed at runtime, and two, that the comparison checks the condition expression, the result of the condition expression. So we've got our two branches here. Surrounding the if branch is a jump to the else branch and a jump past the else branch. And then the else branch is really, all it does is, since we know that the next instruction is going to be the end of the if statement, then we just can avoid this branch, avoid having this branch here. Basically, the next thing it does is go to L1, which is the end of the if statement. All right, questions so far on this template? Okay, so So here's a little choose your own adventure. Should I show an AST and show the code generation like I did with if statement? Oh, okay. So yeah, let me show an example. Yeah, let me show an example. So somebody asked if you go into the else branch, how does it skip the if branch? So let's look at an example of this first. So somebody's asking about if else. So hold the question on if. You mean else if? Do you mean else if? Yeah, hold that question for a second. That's a really interesting question. Hold that for a second. We'll see why that works out. We'll see why that works out. But hold that question and ask it after I go over the example for if then else. Then we can look at what else if, how that works. So yeah, that's a good question. Okay, so here's my example. I just have a condition here where in one branch I set x to 23, another branch I set x to 42. So the code looks a bit large, but just recall that we're passing off the code generation responsibility to other functions. So it's our if then else statement code generator is really just going to be doing 5-10 lines of code. So okay, here is the if then else statement. I know it looks really large, but let's break it down. Let's kind of reverse engineer this template a little bit. The first thing we do is we generate code for the expression. So in this case, we're just evaluating that con variable. So all it does is it pushes that value onto the stack. And then once we're inside our if then else statement, we get that value into a register by popping it from the stack, like we talked about with expressions. And then here is the next part of our template, the compare and jump. And this works just like the if statement, except in this case, the jump is going to be used for the else branch, not for the end label. So just like before, we need to generate a new fresh label. So we generate a fresh label L0 and emit our compare and jump. So up to this point, it's identical to an if branch. So is everyone with me on this so far? Any questions about this so far? It's identical to the if branch at this point. Okay, so just like before, we also generate code for the contents of the if branch. And remember, we do this by just calling codegen statement. We don't have to worry about what kind of statement it is. We don't have to worry about multiple statements. We know that there's just one statement in the syntax that we just dispatch the responsibility of generating code for that. We just dispatch that to codegen statement. Okay, now here's where it gets different from a regular if branch. Instead of just, so if we were to remove this code, it would look basically like a regular if branch. For the else branch, what we need to do is we need to emit an unconditional jump at the end of the if branch, which will bypass the else branch if the if branch were taken. So maybe another way. Yeah, okay. So somebody's asking to see the source code host. So here's the source code. Another way to look at this is so yeah, let me rewrite this in using C goto style, spaghetti code style. Somebody asked, why are go-tos frowned upon? There's a lot of writing on this. I guess, yeah, I don't know. I think when you don't have go-to, because it doesn't take advantage of the like structured code. But if you look online, I think there's like maybe there's go-tos considered dangerous or something. Yeah, there's a lot of writing you can read on that. Okay, so here is effectively, let me double check this, that I got this right. Oh yeah, else branch. So here is in C, the another reason for it is that go-tos, it makes it difficult to reason about what code is being executed if you use a lot of go-tos. It's sort of, I think it's probably just easier for humans to abstract away blocks of code rather than thinking about whether any go-to can jump to somewhere in any code block. I mean, they certainly have their place. They certainly might be needed in certain cases, but usually you won't need them. Okay, so here's an equivalent in C that looks a lot like the assembly. We test the condition, and if the condition is false, we jump immediately to the else branch. If the condition is true, then we don't do this go-to, we execute the if branch. And because here, if we didn't have this go-to, then after we execute the if branch, we'd start executing the else branch right after it, which as we talked about, that's not the behavior that we want for our design of an if then else statement. We want them to be mutually exclusive. So to ensure that mutual exclusion, this go-to ensures it. So somebody pointed out, very astutely, that with no jump, it's almost like a switch without a break. So that's exactly right. One way to implement a switch is to, the way a switch is implemented is you basically jump. You have a jump table to a bunch of statements, and the break ensures that you're not going to fall through to the next case. And so there's this principle that in coding that when I showed the for loop, that you can write a for loop with a while loop. There's certain constructs that can be rewritten or desugared into other constructs. So for instance, here, without having compound statements, I can implement similar behavior using go-tos. Okay, does this make sense so far? Okay, great. So the assembly code version of this is very close to this, at least in terms of its structure. It's close to this. The way we do the comparison is using, we generate the expression and then use compare. But the go-to translates to a jump, an unconditional jump in C. In this case, we use the compare conditional jump to implement this statement here. And then whatever the body of the function is just whatever the body is. We don't care what it is. That corresponds to this x equals 23. And then we jump past the else branch using this jump here. And finally, just emit the code for the else. So we need the label of the else, and then we just call out to codegen statement to generate the code for the actual else branch. And finally, we emit the label for L1. Kind of making sense? You may need to sit down and kind of work with it a little bit. But once you kind of get this template burned into your head, you'll even be able to look at assembly code a little bit and say, well, oh, okay, this looks like it came from an if then else statement. Questions on this? Making sense so far? Okay, so one little wrinkle with this is what's not seen in this in the assembly code is that the compiler needs to create fresh labels, as I talked about before. That gets a little trickier to reason about here because we're generating a jump to, or where is it? We're generating the jump before we actually have the label. We're doing that twice here. So our compiler not only needs to generate the fresh label, but we need to hold on to that label until we actually emit the label itself. So that means your compiler, when it generates this jump, it's not going to just generate a fresh label and then generate the jump. We need to save the label in a variable in our compiler so that once we're past all the recursive statement generation, then we can emit the label itself. So hopefully this is clear in the instructions for the project, but just keep that in mind when you're writing this, that you're going to have to hold on to that compiler in the same way that we generate the offsets and then hold on to those offsets in a table. In this case, we don't have to hold on to it in a table. We can just do this within the same coordinate statement function. But it's the same idea that the compiler is holding on to some information behind the scenes that you don't actually see in the output code. It's just to be able to record information during compilation. Okay, so I think that's enough of an example for this. Is any other questions on? Oh yeah, so somebody asked about Elsif. So this is a really good question about Elsif. Let's think about how Elsif works. So somebody pointed out a good point here about Elsif statements. So let's take, now let's do it here. Let's take an Elsif statement. Okay, so one of your classmates correctly points out that you can rewrite this like so. In fact, I could even rewrite it like this without the curly braces, right? I can write it like this. It turns out that these two programs here, the way I've written it, are identical programs. The only difference is white space here. There's a new line character here. It's the only difference, right? And if I write it with the curly brace version, the only difference is that I have a compound statement for my else versus a single statement versus an if statement inside of my else. So this pattern here of using else ifs is actually not something that is defined in the language. Okay, I don't have the, well, if you look at the syntax of, if you remember the syntax of, I'm gonna actually get the syntax of the language. So somebody's asking, does else if exist in simple C? So just like in C, simple C and C don't need to explicitly provide syntax for else if. So if you look at our syntax for if then else, there's no explicit else if construct in the language. Instead, what's going on is that statement can also be an if statement. So if statement is an if statement, then what you'll end up having is an input program where the else is followed immediately by an if keyword. And even though it looks like a kind of separate construct in the language, what's really happening is that the if statement is nested under the else if. So if we've got our supposed else if statement here, the syntax tree for this is an if then else statement where one branch, is this assignment or whatever, one branch is whatever it is inside. And the else branch is just another if statement. And that if statement contains some branch. So unlike something like Python that has an elif keyword, there is no else if construct in C. The else if is a lie. There is no else if construct in C. It's really just an else branch that happens to have a single statement in it as its body. And that single statement just happens to be another if statement. It would be no different if this were like x equals 42. This would just be an assignment statement instead of an if statement. But it's such a common idiom in programming that we even use white space to make it look like this is not even nested. So if you've got multiple else ifs going on here, then we write it in the style we write it, we don't actually do indenting to show the nesting. But if we look at the syntax of this, it's actually a bunch of nested if then else statements and so on. Great, glad that have some of you, for those of you who haven't seen this before, this is, yeah, it's not something that can be even like easily understood without understanding like syntax, code generation to some degree. But yeah, that's what's really going on with else if. There's really no else if construct in C or simple C. Yeah, so if you have a bunch of else ifs, it's really just a bunch of else's on nested. It's a bunch of nested if then else statements. And there's, we didn't go over it in this class, but if you look at the Dragon book, there's this, well, maybe this is not important to talk about now, but there's this syntactic issue of having, figuring out which else matches which if branch. Actually, this is kind of a different issue. So maybe I won't, let me forget about this. Let me not talk about this. If you look in the Dragon book, you'll see the issue with when you have nested ifs and if then else statements. You have to make sure you're matching the else with the right if branch, but that's a different problem here. But yeah, it's just a bunch of nested if then else statements where you happen to put the, so some languages like Python have an elif keyword, which in that case, the syntax is different. It really is not nested if then else statements. They've got it's kind of like a switch. It's very much like a switch, where if you have an elif, there's a list of elifs. It's an if followed by elifs, a list of elifs, and then an else optionally at the end of that. But in C and simple C and C++ and Java, there's no else if construct. It's just nested if else statements. By the same token, there's nothing stopping you from saying something like this. You can do this as well if you want. It's the same idea, where it just so happens that the one statement that we have under the if happens to be a different if statement. Oh, by the same token. Oh, good. Yeah, I made an accidental pun there. Yeah, so somebody is already pointing out that this is like a Boolean and we'll get to that. We'll get to that for sure today. But yeah, this is just the difference between the white space. The white space is irrelevant to the meaning of the program. But we as users of the language use that white space to help us, see the code and reason about the code. But yeah, having an if followed by an else keyword is no different from just having an if followed by an if. So you can write very kind of terse, confusing code in C like this. I mean, this may look confusing. I'm actually making sure in my head now that this is right. But yeah, this looks very confusing, but this is totally legal, and you can chain together as many if statements as you want. Very hard to look at, very hard to think about what this code does without having some white space and layout. That's kind of the human interface element to programming. It's even if it seems like a very mechanical exercise, but there's still so somebody says it's horrible. Yeah, it's horrible. It's very horrible. So it'd be way easier to write it like, oh no, that's not right. That's not right. It'd be way easier to see it if we write it with nice. So actually, one kind of code style rule is to never have single statements under ifs, with the exception of Elsif. So if you look at style guides, like Google has some very nice style guides for various languages like C, C++. Java has like style guides. They will tell you never write if statements that have you have a compound statement under it. So like never do this. Unless, so the one exception is if you're doing an else if. So else if is so kind of idiomatic in C that we don't even see it as a nested statement. And so this is the one exception to that rule. But the general rule is like, this is bad, don't do this. Instead, always put braces. And the particular style I use is to put the close brace on the same line as the else. But there's lots of different, God, go on Stack Overflow and look at people talk about curly braces. I mean, it's unbelievable that the most insignificant things can warrant the most debate. But yeah, but this style is actually a really useful style. The reason is that if it's very easy to mix up the white space with what actually is nested under the else. So if I say something like this dangerous function that shouldn't run when cond is true. So if I have a program like this, if I added this later, this dangerous function, I may just at a glance think that by having this indentation, this is only run on the else branch. But as you now see, this program is equivalent to this program. You guys see that? Same program, right? But as the name clearly shows, I will get owned if my program will be ownable if this function is run outside of the else branch. It should only be run in the else branch. Yeah, this is the sole reason. Yeah, all coding style is really just for human error. Make it easy, make the code more kind of legible, more easy to think about for the reader. And you may think that this is a kind of a minor point, but there was a case of this. It may not have exactly been. Let me actually look this up. I had a link to this one year in my class, but let me see if I can find this again. Let me see if I can find the code. There was where was this? There was a serious go to fail. That was it. Ironically, the code in question was called go to fail, and it was a fail of the same kind that I'm showing you here. Okay, so here's the code. Yeah, this is exactly it. So this happened in real world code, where if you look here, the developers didn't bother having these. They didn't follow this style of curly braces because, you know, why would you? You know, there's one test and one go to, and it turned out either by accident or perhaps some very clever adversary managed to get this go to fail inserted. So at first glance, it looks like that this go to fail is part of the if block. But as now you all know, you know how compilers work and how the C language works. You now know that this go to fail, exactly. So this go to fail is unconditional. And the problem is that this code here is involved in validating an SSL certificate, verifying an SSL certificate. So this means that the that if so when you go to a website, the verification of the SSL certificate is a way to prove that that website owns that certificate. It's a way to actually authenticate that you're talking to the server that they claim it is through the SSL certificate infrastructure. So if you trust the SSL certificate infrastructure and you go to a website and you trust the crypto that's going on behind the scenes, the public key crypto, then you can trust that that server and only that server holds that private key for the SSL certificate. But your browser needs to check to make sure that that certificate, they need to actually check to make sure that you need to use the SSL protocol to make sure that that server actually holds the certificate. This little mistake that is related to this coding style and syntax of the language caused that check to always be skipped. And I think what ended up happening, if I'm remembering right, is that it made sure that your browser was never actually verifying the SSL certificate. So I can't remember all the specific details. I think that, so this is what ended up happening. If somebody at, say, if you were at a cafe or a public access point, there's really nothing stopping the provider of your internet from sending you to a different location for, say, Google.com. They can trick you unless you take extra mitigating steps. They can trick your machine into, or maybe not trick it, but they can tell you a different address for Google.com. But the way we can protect against that is through public key crypto, having a certificate that we are sure that only Google has, and that our public access point, we're pretty sure don't have that. And so HTTPS will send you a warning to say, well, that person doesn't have the certificate that I think is Google's certificate. But if you have a bug in that check, then you won't know that actually is an imposter, a self-signed certificate. Someone else made their own Google certificate. So this little tiny style bug turned out to be a serious security vulnerability. So this is like a horror story to remind you to just put curly braces around your if statements. You don't want to be this team responsible for this code, for this little tiny mistake that turned into a serious vulnerability. There were some rumors at the time that this was intentional, because one kind of conspiracy theory is, why would you ever put two go-to fails? There's a maybe reasonable explanation that somebody was editing this code and deleted an if, but kind of forgot to delete the go-to fail. And it's kind of like when you write the twice, when you're writing. It does seem odd, but you can imagine if you're mutating, you're editing the code over and over and over. Just like when you're editing text, you may leave you may say the twice. I do this all the time when writing. I'm editing code and I leave in duplicates because it's, I think humans kind of deduplicate automatically. So you may be quickly looking through this code and just quickly scrolling through it. I mean, it's very hard to see that there's a duplicate here. Anyway, that was some conspiracy theories at the time. Who knows what really happened? Maybe you can take a look at the commit history for this. I think it's public code. And it caused, I think, iOS and OS X both used this code, and it was a serious bug at the time. So anyway, use curly braces when you have conditionals, unless you're doing an Elsif, because it's such a common idiom. And now you know what's actually happening behind the scenes with that. Okay. Let me get back to where we were. Okay, any questions so far? These are some fun little tangents. I hope these are fun. These are fun tangents. But any questions so far on this? All right, great. I'm glad you like the tangents. I think the tangents are probably more interesting than the actual content, of course. But I'd like you to be able to compile this, code up your compiler. So let's get back into the details of this. All right, so that's if then else. That's Elsif. So now you know really what's going on behind the scenes with an Elsif in C and C and C++ and Simple C. Other languages, as mentioned, like Perl and Python, have these baked into the language, baked into the syntax of the language. All right, so let's look at while loops. A while loop. Okay, so what's the behavior of a while loop? So can anyone kind of describe it to me in natural language? What is the behavior of a while loop? So we have some condition here. Actually, let me get the while loop example. So describe for me the behavior. Yeah, less fancy for loop. Less fancy for loop. Okay, so you're defining it in terms of another construct. So what's a for loop do then? A segment of code continually runs while a condition is true. So repeat something while something is true. Yeah, those are good intuitive things. Good. Okay. So knowing about how a while loop works kind of intuitively, informally, what is the result of this program? What does it return? So I'll give you a second to kind of look over this. Yeah, somebody has another way of looking at it. Check the condition, run the statement, go to the top and repeat. So what does this program return here? So somebody says 3. It's a for loop. So people keep saying for loop. For loops don't exist in Simple C. But I see what you're saying. So the semantics of a for loop is like step through each, iterate through each number one at a time. Typically you're counting, going through, I from 1 to n, and you're stepping over each I typically, but that's only one way of using it. So okay, so somebody so somebody said, so got some other answers here. So 72, the result here is 72, and somebody pointed out an interesting formula here, saying, well, it's 24 times 3 equals 72. That's kind of interesting here that you can define this while loop in terms of just a single expression, right? That's we'll talk about this a little bit when we talk about program analysis next time. But one task of trying to understand what a program does, particularly while loops, is to see if we can come up with an expression that defines the whole loop. The technical term for this is an invariant, something that's always true for every execution of the loop. If you can do that, then you can actually define, it's easier to define what the program does. But anyway, another tangent for another time. We have a scheduled tangent next week on program analysis. Okay, so good. So yeah, we got there. We got there eventually. So what this code does. So looking in detail about the semantics of a while loop, in this case, the behavior of it, is that we have 2 variables defined at the beginning. Count is 3, x is 0. So somebody asked, would a good comment for this be the expression, hey, this is computing x 3 times 24. Yeah, that would be a good comment. And in fact, you're the chair of this very department, Dr. Levins, is one of the things he's famous for is something called Java modeling language, where in comments, you put math specifications of what the code does. And then through that, you can actually do a bunch of things. You can automatically check that the code is doing what that comment says it does. You can prove that, and you can, by composing these they're basically math specifications. They're written in comments, but they actually have meaning as math specifications, and you can actually use it to verify that a program does what you think it does. So it's a way to actually match specification to the implementation of the code. And so yeah, he's well known for this. You can look up JML or Java modeling language to learn more about this. But yes, that would be a good comment. And so this is, and you can even, you can do this to some degree with assert statements. So not completely. So assert is really a runtime check, but you can use it to say like, well, I think that X is going to be 72 at this point. This is not, quite the same power of being able to specify, well, this whole function does this, that's with a general math expression. But with an assertion, you can insert these kind of checks in the code, and assertions both document behavior that you expect and can actually be used to insert runtime checks so that the program will fail if this assertion doesn't hold. Anyway, yeah, so there's actually a good 1 or 2 page paper on this assertion style where this notion of prerequisites and post or pre and post conditions for functions is sort of talked about as a kind of coding style. Java modeling language makes that possible to do mechanically, where you can bring in automated techniques for proving that the specification is matching the implementation. Okay, so the behavior of this is we start with count being 3, x equal to 0, and we loop until count is 0. Till count evaluates to false. I didn't want to introduce a lot of extra expressions here, so I'm just testing count itself, and 0 is false. So for every iteration of the loop, I add 24 to whatever x was before, and I subtract 1 from whatever count was before. So if we were to unroll this loop, we would get, we'd start out with x is 0, but then we'd get x is 24, count is 2, x is 48, count is 1, x is 72, I think, and count is 0. And then for that final evaluation of count, we would find that it's false and then exit the loop. One really, really critical thing to keep in mind is that it's not just the body that is being executed again for each iteration. It is the expression and the body that's being reevaluated. That's how we're able to check any changes that are made in the while loop. So if we only re-executed the body and didn't reevaluate the expression, then this expression would remain 3 forever, and we'd end up with an infinite loop. And so this is one little gotcha when you're implementing your code generator. Make sure you're jumping to the right place when you're doing this. But I'll show the code generation in a second. But yeah, this is one thing to keep in mind in C, that this expression is being reevaluated every time you iterate the loop. And so that's kind of, that can lead to some kind of tricky gotchas in C. So if I say I have a program like this, where I'm also incrementing the counter inside of the expression, in C, you're allowed to change variables. You're allowed to have side effects in C, where the expression itself may alter some state. It's not just a check of state. It may actually alter the state. So this is actually kind of a tricky little exercise for you guys. What's the result of this program? What will X be at the end of this program if I got it right? What do you guys think will be X at the end of this? This is a tricky one. So somebody asks, infinite loop? Yeah, I think it's infinite. Because so this is going to set count to 4. This is going to set it to 3. This is going to set count to 4. And so this behavior is really critical to understand when writing C code, that expression is always evaluated. This is maybe a more obvious case, but if we have a case like, this, where we wanted to compare it to 2 or wanted to compare it to 0. Well, let's say we wanted to compare it to 2. Then in this case, the loop will terminate because eventually the count will be 2 and then it'll stop. But just removing one little equal sign, what'll happen with this loop? Again, we're going to get an infinite loop because here we're assigning count to 2, and 2 is always non-zero. It's always true. So this is again going to be an infinite loop. So this this kind of side effect behavior where you can not only test the state but alter the state at the same time. This leads to a lot of issues in C as well, particularly this equal sign thing. That's why another coding tip for C and C++ is to put the constant first. So you saw this in my code. This is something I learned actually from my advisor. It was kind of a system researcher. This is one little coding trick where you put something that can't be assigned to on the left-hand side of a comparison. So that will, it's a very kind of little trick where that'll actually force the compiler to check to make sure you've used equality versus assignment. Okay, all right, so that's the behavioral while loop. The main thing to keep in mind is that we're reevaluating this expression every time we iterate the loop. And as a little observation from the assembly side is that a while loop is really just an if statement with an unconditional branch. So let me put this back to what it was before. One way to desugar or translate this while loop into other C constructs is to write it as an if statement but make a special label for the if statement, that has basically just go to the top of the loop, which is go to the stuff before you started evaluating the expression. So this code here, I think, is equivalent to the while loop. Let me know if you notice anything wrong, because I wrote this down yesterday, but I wasn't checking my notes. I'm pretty sure this is equivalent to a while loop. Anybody notice anything different here? I think this is right. So when I say that an if statement is basic, or a while loop is basically an if statement with an unconditional jump, what I mean is that the one way to implement a while loop is to basically implement it the same way you implement an if statement, but just have this additional go-to at the end of the if branch. One kind of simplistic way of thinking about this is, well, this is what's kind of going on, right? The top of the loop is the beginning of this expression statement, or the beginning of this body. But actually, the while loop, we need to, at least in C, we need to reevaluate this expression. So that means the label is actually before the evaluation of the expressions. Yeah, so somebody already points out in an if statement, we only need one label to get us to be able to jump conditionally past the if body. For a while loop, we need that same label, but we also need an extra label here at the head of the loop to recompute this. So the head of the loop is the part where you compute the expression and then branch, just like an if statement. So I already went over this example. Here's my equivalent version, same thing. So there's a very academic term here called desugaring, where one way of viewing certain constructs in the language, like you could think of a for loop as syntactic sugar for a while loop. And this just reflects the notion that other constructs in the language can be used to implement more sophisticated constructs. And some academic researchers try to think about what's the core language in which you can implement the rest of the language. So somebody asks, wouldn't it make sense for the compiler to never allow assignment in a conditional statement? Yeah, I mean, this is a language design question. There are certainly those who view there are some languages that not only don't allow these kinds of side effects, but they don't even allow you to change state at all through an assignment. Once you once you bind a symbol to a value, there's no way to rebind that. You can only update its state through constructs. But then there's the other side of it, which is, well, there's billions of devices running C. C has been around for decades, and this is the behavior of C. C++ adopts this behavior because it's backwards compatible with C. So it's really, yeah, this is more like a taste thing, or yeah, there's arguments on either side. So on one side, yeah, so there's less freedom. So maybe it's convenient to be able to allow a while loop that does assignment and testing. And there are certainly legitimate cases of this and real world code that does this. And there's the other side of it that says, well, if we make this restriction, the less freedom part, then it's easier to reason about the code. Maybe it's easier to look at. Another way to look at it is you could also just yourself have a rule where you never allow assignments in conditional statements, and then just make a check, a simple syntactic check that says, hey, you have, you can do this syntactically, the AST. And if for those who are interested, you could actually take the simple C AST and write a little tree walking algorithm that checks whether, well, we don't actually have this in simple C, but you could add it to the language in the syntax, add, allow an assignment expression here. And then just write a syntactic check that says, well, I never want to allow assignments in, I want to warn the user when that happens. So that's a very simple syntactic check to do. So yeah, it's different philosophies about language design. There's definitely multiple camps on this. But I think, modern languages like Java do not allow this. They don't allow assignment inside of an if statement, but I think they still allow increment. Do they still allow? So I'm not remembering Java exactly. I think they still allow increment in a, but anyway, yeah, this really depends on, this depends on a lot of things. This is another debate that's probably going to go until the end of time, as long as programming languages exist. But certainly, from my point of view, it is actually easier to reason about it if you just don't allow it. Generally, when I write code, I don't use these tricks. I write the code, I make the code longer, so it's just easier for me to look at. It's kind of the similar idea to always putting a curly brace. I mean, yes, you can omit the curly braces because it's, it can take a single statement, but it's just kind of useful style to do it. But maybe, maybe there are exceptional cases where it makes sense to allow it to not, to allow that freedom and just say, well, I'm not going to use that except in some exceptional cases. But yeah, I don't know. I'll let you guys think about it. There's lots and lots of debates on language design that if you're interested, send me a message. I'll send you some, talks by people about this language design stuff. Okay, so thinking about this as basically just a desugared into a construct that uses if statements. Here is the assembly code template. So the first thing to notice is that right here, this is identical to an if statement. And in fact, and this part is identical to an if statement. The only differences are that we have this unconditional jump that we insert after the if branch and a label to go to the head of the loop. That is everything from before, including the condition expression evaluation, including the comparison and jump, but also including the condition expression evaluation. So if you kind of like squint a little bit and go back and look at this, you can make a little comparison between the if branch and, yeah, exactly, this go-to example. Make the kind of comparison there that we've took the assembly code for the if branch and basically just inserted a label for the head and an unconditional branch to the head at the end of the body of the if statement. Questions? Making sense so far? You guys have a example of this right now from the website. on the project website, so you can evaluate this yourself. So just some things to keep in mind when you're doing this. Always keep in mind that the compiler is generating code that is equivalent to the input program. It's not actually evaluating the code. So just like we showed in our AST examples, when we walk the tree, we're not evaluating that code. We are basically just printing out assembly code. And when we're thinking about how to write that compiler, we have to think about the guarantees in terms of that, the guarantees in terms of what the assembly code is being generated, rather than how the runtime behavior of the program is for a particular program. Maybe this isn't an issue for this quite as much as it was for expressions, but yeah, just keep in mind that you're generating code. So if you need to generate an if statement, you're going to have to create a new label and then save that label in a variable. So you're not saving any state about the input program. You're saving state that helps you generate code. Okay, that was very abstract. I don't know if that's helpful, but yeah, just keep in mind that you're generating assembly code, you're printing it out, and try to avoid the confusion with what the runtime behavior of a particular if statement is versus how do I generate code that's going to be equivalent to the input program. If you follow these templates, they should be equivalent to the behavior of these three constructs. And yeah, generating fresh labels. And just like before, we talked about this already, specification of, make your components, specify those components, just call out to codegen expression and codegen statement. Another thing to keep in mind is the compiler is not going to complain to you if you use the wrong statement kind. So just if you have bugs, double check that for if statement. So if you're taking the kind of lazy way, which is what I did, copy and you're cutting and pasting the if statement to the while loop, make sure you actually use the right construct. You're not getting the if statement construct, you're getting the while construct. So I made that mistake last night when I was coding this. So just make sure I would suggest writing it from scratch for each one instead of doing that. All right, questions on these control flow constructs? Okay, so now that we understand control flow constructs and how the kind of simplest template we can have for generating assembly code for control flow constructs, now we can look at Boolean operators and see why Boolean operations don't work the same way as other expressions, arithmetic expressions, at least in this language, they don't work the same way, and why I separated them into two different projects. So the Boolean operators go with control flow because it turns out that we can actually implement Boolean operators using control flow, using compare and branch, rather than using a particular machine code operation. So you can certainly imagine a language where logical operations are bitwise operations, and perhaps you could do that. But in C and simple C, the way Boolean operations are there's a distinction between bitwise operations and Boolean operations. Even though C doesn't have a Boolean type, they still have operators that are the logical and logical or the Boolean and Boolean or. So the way we're going to implement this in simple C is we're going to use compare and branch. So as one of your classmates actually already pointed out a while ago, that we can take this same notion of desugaring and apply it to Boolean operations. So in the same way that a while loop can be desugared into an if statement with a branch, a Boolean and can be desugared into nested if statements. And this makes sense, right? Because in order for this body to be executed, both the A and the B have to be non-true. So we have to check A, non-zero, check if it's true, and then move on to B, evaluate that, check if it's true, and then only after passing those two gatekeepers can we execute the body of the if branch. By the same token, this if branch will, this if condition will check A and only execute its body when A is true. And then the first thing we do in that body is to have another if statement that checks whether B is true. Make sense so far? Okay, so I'm dumping the template onto you, but let's go through this carefully. So it works a whole lot like what a nested if statement would look like. The reasoning is a little tricky to go through. It's actually a little tricky for me to explain too, because we have to like think about, yeah, it's very tricky to go through. But let me try just talking through this template, and then maybe we can I'll take questions, and then we can go through some examples and see if we can understand this better. All right, so the whole idea, remember, is that we need to make sure that both the left and right operands of the Boolean AND, we need to make sure that both of them are non-zero, and only if both of them are non-zero will we execute the will we return the result being true. So we can think of this as an if statement where the body of it assigns the resulting expression to be true. So somebody's asking, Boolean ANDs only work in conditional branches, correct? So actually that's not quite right. Boolean operators are expressions, so they can be used wherever expressions can be used, including in assignment. Okay, yeah, so one thing that's, yeah, this makes this tricky to reason about what the code generation looks like for a Boolean operation. So in one sense, it's an expression. So we need to treat it like an expression where we evaluate its two operands and then return the resulting expression by pushing its value onto the stack. And actually, I didn't put that in this template here, but I probably should do that. Let me actually add that push so it looks like a complete. Well, yeah, I mean. You have to do more to make this an expression, like you have to evaluate the left operand, but I'll just I'll put that in a comment here as well, just to make that clear. So yeah, this is what's really confusing about the way Boolean operations work in the C-like languages. They are at once an expression where you have to evaluate both operands and then return an operand. It results in a value that you have to save somewhere and use for whatever is using that expression, whether it's an assignment or whether it's an if statement. We need to have that expression for the if statement. So if you recall our template for the if statement, which I can show here on the right, or say the while loop, we have to first evaluate the expression so that we can compare that expression to zero. So a Boolean operation is an expression in that it evaluates its child operands and then takes the result and pushes that onto the stack. But in order to compute that result, it uses control flow. It uses compare and branch to do that. So on the, let me regenerate this. So the kind of outer structure of this template is the same as any other expression, where the first thing you do is you evaluate the left and not right operand, and according to the invariant I've recommended to you, that gets pushed onto the stack, and then you have to pop it into two operands, A and B, and then at the end you push the result onto the stack. So this kind of outer structure here is just like every other expression. But the inside of this template is much more like an if statement, an if branch, or nested if branches. Does that make sense so far? So you kind of have to sit down and reason this out a little bit, compose these pieces together. But think of this as an expression in that you evaluate both operands and return an expression and provide an expression to the parent of this expression. And then on the inside, in order to actually compute the expression, instead of calling a machine code, instead of calling a machine instruction, we use a compare and branch in order to assign the value. Does that make sense so far? That it's this kind of hybrid between an expression where we need to provide a resulting value and control flow where we use compare and branch to compute that value. Making sense so far? Kinda. Okay. Okay. So let's ignore this highlighted part and just view it as any other expression where it's an expression that evaluates both operands and then puts that result onto the stack. So yeah, when you go to digest this, separate that in your mind. It's like keeping your peas and mashed potatoes separate. Separate that in your mind for a second before you think about them together, and think, well, okay, this is the part of it that's like an expression. Now when I'm thinking about how to compute that, yeah, I'm trying to think. So the thing is, I don't even know how to do a diagram for this because all of this is in one code generation function. Well, actually, yeah, let me attempt a diagram to at least let me see if I can at least make this. I can actually, even though there's nothing with the syntax tree that is really relevant here, I can at least show you the different pieces of this operation graphically. How can I do this here? Oh, that's not good. What happened? Oh, there we go. Okay. Let's see. How do I explain this? So if this is our template, any expression needs to any expression in Simple C, the way I've recommended you implement it, has to get the operand values first. That's what any expression needs to do. With me so far on that? And the very last thing it needs to do is push the resulting value of that expression. That's what it has to do. The difference comes in how we compute the resulting value. For arithmetic expressions, there's machine code that there's a machine instruction that will just do add for you. So you can literally just do like add RBX, RAX, and like done. But there's no machine code instruction for a logical Boolean operator. Basically, yeah. There's no necessarily machine code instruction for that exact operation as we want it implemented in C and Simple C. So instead of having that one operation, we need to emit a bunch of assembly code that's going to guarantee that it has the behavior we want. And so that assembly code is going to look a whole lot like, for conjunction, it's going to look a whole lot like a nested if statement. So if we think about the where's my example here? If we think about, oh no, it's here. If we think about the desugared version, we're going to basically make the assembly equivalent of this code. So that's why, I mean, it helps to first understand the assembly code equivalent of the if statement, and then go into the Boolean operations. It'll be much easier to think about if you already understand the kind of template for if statements. So within the kind of expression parts of this code, we need to
generate code that's going to give us the logical conjunction behavior that we want. Making sense so far? Okay, so analyzing was good. Okay, good. Yeah, so you can think of this as just like putting a machine code instruction here, except we don't have like logical and. We don't have a machine code instruction for that. For a couple of reasons, we don't have that, which I'll hopefully get to in a second. So one of them is short circuiting in C. So if you're familiar with short circuiting, that's one. That behavior is one consequence of the way this is implemented. Okay, so let's think about what this logical AND operation does. Semantically, what it does is, so informally what it does is it first evaluates the left operand. And then if that's true, it evaluates the right operand. And if that's true, then the resulting value is also true. So another way of looking at this is this is like RAX equals, let's say RAX equals A, RBX equals B. And then we evaluate RAX to see if it's true. We evaluate RBX. And if it's true, we assign RAX to 1. Otherwise, we assign RAX to false. Let's look at disjunction in a second. So disjunction, let's understand conjunction first, and then disjunction works in a similar way, but the logic is confusing to work through. So this is effectively what we're doing with, well, actually, let me make this simpler. So let me make it match the template a little bit closer. So we only set RAX, the result, to 1 if both of these conditions pass. Otherwise, we set RAX to 0. But we want to make sure that, just like for all of this assembly code, we use basically a goto to skip past the else parts of our code. All right, so hopefully this is a little clearer. So RAX, we set whatever A is, whatever B is goes to RBX. We evaluate each of them one at a time. If the first one is true, then we go to the nested if. If the second one is true, BX, then we assign the resulting value to 1 and then branch to the end. If either of these are false, either RAX or BX are false, what's going to happen? We're going to go to the end of the if statements and then set RAX to 0 and then continue on with our code. So this is kind of like the pseudocode for A and B. All right, making sense now? I think this is, okay, I should have done this originally. This is a good way to, because I'm now realizing that because assembly is so unfamiliar, that writing assembly like C is actually a much more, is actually a much better way to do this. So let me put this here in notes or something. So I'll format this later. Okay, so this here is our, because we don't have a logical AND operator the way we want it to be defined, we make a definition of it. And our definition, this is the pseudocode for it. So that is exactly what is going on here. The stuff before and after it is what we just have to do for any expression. So by the end of this code, our AX is going to have the resulting value, just like for add. The right operand is going to have the resulting value. The right operand to add is going to have the resulting value. Here we're going to, again, we can override. I mean, we can use any register we want, but to make it similar to other instructions in machine, we store this in RAX. All right, so I think most people are on board with this now. So let's walk through the assembly code, and let me keep the C code up next to it so we can see what's going on here. So these here are part of the evaluation and storing it into RAX. This compare and jump is saying, actually, let me actually put the label here. So this is L0 here. So this first compare and jump corresponds to the first if statement. So if RAX is false, then we know that the entire logical operation is already false. We know that, by the rules of logic. If the meaning of a logical AND is that if either of them are false, then the entire expression is false. So we just immediately jump to the L0 branch, L0 label, and just set the result to 0. The next thing we do is, so if this is not false, then we go to the nested if statement. The nested if statement, again, compares the value of the right operand and checks, is it false? Is it true? If it's false, we know that the entire logical AND is false. So we jump to L0, just like we did before, to set the result of the expression to 0. If it's true, then we want the assembly program to not jump and instead move to the next instruction, go to the next instruction, which assigns the result of the expression to true. With me on this? So it's effectively this code, but in assembly. How's this looking so far? Mostly with me right now? Good, okay, great. Now, so a nice little tangent here is that if you've ever heard of short circuiting in C, I don't know if you guys were taught this in CS1. Short circuiting in C means that in C, if I have this, so some people learn this, intro to C. So short circuiting means if A is false, then I don't bother evaluating B, because I know that we know that the entire expression is going to be false, so there's no reason to evaluate B. Now, again, this comes down to C's side effect behavior, that if this were, say, an assignment here, if this were like assigning count to 3, then what would happen with short circuiting? If A is false, and I said count to 2, and A is false, A is 0, what would count be assigned to in this program? What would the result be for count? It would be 2. Yeah, good. So this is kind of, you have to define this as a language designer. What does it mean to have side effects in an expression that's used in a logical AND? Do we execute it or do we not execute it? And C takes the close to assembly approach for a lot of its design. And so just as an effect of the way logical ANDs are implemented or can be implemented, you get this short circuiting behavior. It's almost like, I don't know if it was an explicit design choice or not, or if it just sort of fell out of the fact that this is how you would implement logical AND in assembly. And that the consequence of that is that the second expression is never evaluated, or is never evaluated if the first expression is not evaluated. So this now opens the hood on short circuiting, why it works that way, and it really kind of just falls out of this implementation of a logical AND in assembly. You could certainly imagine having a different language where you always evaluate this expression, whether it's true or not. And the way your code generation would work would just have to be different. You wouldn't be able to implement it this way. But let's just focus on the short circuiting C approach. And yeah. Okay, questions on this so far? Oh yeah, this is a good point. So somebody pointed out that if you're doing tree walking or some sort of data structure validation, and your expressions are checking null for nulls in both expressions, as you can look at the chat to see this example, then short circuiting means the right expression won't be evaluated in a disjunction. So yeah, can lead to this again, can lead to this unexpected, what we thought when we were writing the code is not the actual behavior of the program. And so this is why, in the programming languages world, there's a lot of effort to make very formal specifications, very precise mathematical specifications of language. So at least when a machine is processing this language, if we're doing program analysis, we can use that specific definition to make a program that can kind of automatically work with the behavior of that program. And for us as the programmer, it's really important to have this good understanding of the behavior of the program. So when we write code, even if we can still make those mistakes when we write code, we can use good style that ensures that or that helps ensure that we don't make those kinds of easy to make mistakes. Okay. Questions on this so far? Questions on conjunction? So I am now at the end of the official time. So if you need to leave, please by all means leave. I'm going to cover disjunction, and then we'll leave, and then that'll be the end of lectures for project 4. I'll leave the rest for you to figure out. Check the project description for details. Talk to me in Piazza. Talk to me in office hours. But you'll have your assignment later today. You'll have the project 4 assignment. Any questions on this so far, on conjunction? Okay, so let me get into disjunction. Oh, I called it conjunction here, so I had a stupid mistake here. Disjunction with or. So note that it's equivalent. We have a similar kind of desugaring that we can do with disjunction. So the short circuiting also happens with disjunction, except as your fellow student pointed out, instead of assuming that the entire expression is false if one operand is false, with disjunction it's the inverse of that. If one of the operands is true, we can assume that the entire operand is true. So for the sake of time, let's just plop down the template. It looks identical to the conjunction template, except we invert the logic for it. So let me go through it. So well, actually, let me write the C code for it. I think the C code has been very helpful. So let's write the C code for disjunction. So it works the exact same way in terms of control flow as disjunction, except we invert the logic. And I think this is related to that, is that De Morgan's laws, where you negate a conjunction and you get a disjunction? So it's kind of related, it's related to this notion. Okay. Let me actually make sure that this is right. Oh yeah, okay. So here's the reasoning. For disjunction, basically it's equivalent to the negation of the conjunction. So instead of checking whether the disjunction is true, we check whether the negation of the conjunction is false. So instead of checking that the disjunction is true, we check that instead of checking that A or B is true, so this is how our assembly code works. We convert this into checking that the negation of the disjunction is false. So I'll leave it to you to sit down and work through this. This is just, the classic, is it De Morgan's laws? Am I getting the name right? I can't remember. I can't think right now. But that classic logical rule that the negation of the disjunction is the conjunction of the negated operands. I mean, you should know this. You should know this from like discrete 1 and CS1 and stuff. So this is effectively how we're going to implement this in assembly using the same pattern that we use for conjunction, except we have to make sure that we negate the operands and compare and you know, negate the resulting value. So this is effectively what's going on, but let me walk through this operation so that you can so when you walk through it yourself, you can like keep in mind of the gotchas here, what's different about it. It's always confusing to kind of work with this negation and logic. Okay, so let's walk through it. So we have our operands A and B and registers A and B. We again compare the left operand to false, but in this case, we want to check the negation of it. So we jump only when it's not false. So here we're using a jump if not equal instead. So that's how we implement this negation. So instead of compare, you know, one way to do it would be to compare it to true, but you know, we can't do that. We have to compare it to not false in order to compare it to true. So we check the left operand to see if it's true, to see if it's not false. If it is false, then we need to, for disjunction, we need to go on and check the right operand. They both need to be not false in order for the resulting operation to be true. So we do the same thing with the right operand. We check to see if it's not false. If it's not false, then we need to jump. Otherwise, we set the result of the expression to false. So that says if either of the operands were false, if both of the operands were false, that is, both of them were, you know, not false, then we assign the result of the expression to false. Otherwise, we assign the result of the expression to true. I'm having a hard time explaining this. It's very tricky to work through. I think you just need to work through it. A couple examples on paper, just walk through the reasoning through it, maybe rewrite it yourself to try to get it right. But it's, you know, it's very complicated to work through these detailed logic operations. But yeah, this is one way to do this in assembly code. There are certainly other ways to desugar this. You could, you know, duplicate the contents of the if body and you know, you could do it that way. There's other ways to desugar this. This is the way I did it because it's, you know, it's short and it's very close to conjunction. But this kind of De Morgan's law is what's going on behind the scenes to make this possible. Okay, so 2 minutes before office hours. Any questions on this so far? I think this is something where you need to kind of just go back and look at it and step through it yourself to sort of believe that this works and actually verify that it works. You know, maybe I made a mistake. Verify for yourself that this works. But big picture, we are implementing an expression and we're implementing it the same way as any other expression, but we don't have a machine instruction. So we generate basically a set of control flow operations that will assign that will basically implement that logical and or for us. I did not show you negation, but I would leave that as an exercise to you. So it can work the same way where you use compare. So somebody's asking, can compare work with two registers? Yes, compare can work with two registers. That's right. It can. Yeah, compare can work with two registers for sure. No, yeah. So for less than and greater than. So okay. So one thing I want to point out, I wrote this in the project description, which I'll release today. But you don't need to support all comparisons because you can actually, as long as you have less than and equality, then you can write all of the other operations. So you only need less than and equality. By all means, write the other ones if you'd like. It's pretty rote. Once you have one, the rest are easy to write. But one thing to keep in mind is that, you know, take a look at the reference that it's at the end of the It's at the end of the project description. There's a reference for assembly here. Take a look at the JCC, the jump command, which I also, I think I put this in the project description as well. And you can find all of different variations here. One little tip to keep in mind for doing comparison is that just like for equality, we check the negation of it. It may be more convenient to check the negation of less than, which is greater than or equal to. Yeah. So I'll just leave it at that and let you kind of work through it. And we'll see next time or during office hours whether how tricky of a puzzle this is to figure out. Yeah, and similarly for compare, they have all the details here where you can put, here you can put two registers as well for compare. Okay, so it's 1 o'clock. It's office hours. Thanks for bearing with me. For those of you who aren't here, hopefully you'll be able to watch the recording of this. And yeah, I'm going to switch to office hours in a couple of minutes. I'm going to take a 2-minute break and I'll be in office hours. Have a good day. Have a good weekend, everybody. Almost to the end of class. Actually, this is the end of the main material. It's going to be special topics next week. And yeah, we're almost done. All right, guys, have a great weekend. Talk to you all later.